In this video, we demonstrate our visual analytics framework for exploring vulnerabilities and adversarial attacks to machine learning models. After opening the system, there are two views for exploring the attack space, a summary view of the victim model and the data table view. The basic information of the victim training dataset and the victim model is shown in the summary view. In the data table view, we list all the training data instances with columns describing corresponding attributes and vulnerability measures. Users can sort the instances based on values by clicking on the header of the column. Users can explore details of the attack results for a target instance by clicking on the checkbox. We have designed 5 modules for exploring the attack results: the model overview, the instance attribute view, the projection view, the feature view, and the local impact view. In the first case study, we present an example in which a model is used to classify handwritten digits from the MNIST dataset. We use the numbers 6 and 8 as the two classes. After loading the dataset, vulnerability measures for all possible attacks from the binary search and stingray attack are displayed in the data table view. By ranking the two columns of MCSAs for each attack algorithm, we find many data instances are at a high risk of a low-cost poisoning attack, as indicated by the red bars. We also observe that the data poisoning attacks have very little influence on the model prediction performance, as the accuracy and recall values of the model experience little change from the attack. Next, we explore a worst-case attack scenario by selecting the instance with the highest MCSA rating under the stingray attack, instance number 152. In the model overview, the overlapped lines in the radar chart show no performance change in the poison model. By exploring the data distribution in the projection view, we see the poisoning instances span the border region of the two clusters. We further inspect the local impact view and find that the neighborhood of instance 152 has been heavily poisoned, and the poisoning instances establish a connection between the target and two instances in the class of number 6. In the instance attribute view, we observe that for instance number 152, the label has flipped from number 8 to number 6. However, the poisoning has resulted in a very short DBD and a low classification probability. In the second case study, we demonstrate how to use our framework to explore the vulnerabilities of the spam filter. For spam filters, the recall score is critical for measuring the performance of detecting true spam emails. After ranking the two columns of recall, we find the instance 40 could result in the largest reduction of the recall score under a binary search attack. We choose to explore the results of a binary search attack on instance number 40. In the model overview, we see the false negative value representing the undetected spams increased from 16 to 30. When inspecting the projection view, we find that the two classes of points and the poison instances show a heavy overlap, which may increase the possibility of flipping innocent instances. In the local impact view, the outer ring of instance number 40 consists only of the poisoning color, which means it is completely surrounded by poisoning instances. There are also more than 20 innocent instances in this view whose labels are flipped from spam to non-spam, which causes a decreased recall value. We examine the details of these flipped instances in the instance attribute view and notice that most of them are close to the decision boundary in the victim model. In the feature view, we see that the variance is quite large on some words such as will and email, which shows large gaps between the non-spam emails and instance number 40.